Good evening. Uh, so the topic what I'm going to discuss today is wall heat transfer and PCM integration in buildings. So although the wall heat transfer we have studied numerically how to do the numerical simulation. So today we are going to discuss about wall heat transfer and the PCM integration in buildings. Okay. So why wall heat transfer has been added? Because I wanted to introduce the glass and the wall contents, okay, parallelly, so that that also it is studied, and a few concepts on wall heat transfer that we have not studied. We have discussed over uh, the numerical methods. Okay, so there are some then exact methods that we can be discussed. Okay, so today we are going to discuss in that very brief. I'm just going to tell the outline how you can do that, because few solvers it is working based on that. Okay, okay. So steady state model means heat in will be equal to heat out. So that we would have studied, all of us would have studied in our basics. And if it is a transient model, heat in will not be equal to heat out, that we have studied day before yesterday also I told you. So heat in will not be equal to heat out, so there will be a difference, so that will be contributing for the transients. So that is what we have discussed. Okay, so the heat in will not be equal to heat out. Okay, so then heat will be stored. So this will be there in the wall. Okay, so in the wall, when the heat is entering in the wall, so it not be equal to leaving. Okay, so because of that, transients will be there. So we are going to study what is the effect of transients. Okay, so the effect of transients is it depends on the wall thickness. Okay, if wall thickness is more, okay, if you have a heavy wall thickness, so if technically speaking, if heat capacity is more, okay, heat capacity means it's a product of m into cp. The mass of the wall is more and the cp is also more. Okay, so what will happen if I am giving a temperature signal like this, varied temperature signal like this? So at the output I'll be having a damped signal like this. Okay, so here you can see the amplitude is very much high, and when it comes here the amplitude is smaller, and the peak also it will get shifted depending on the mass heat capacity. Heat capacity m into cp. M into cp means it is a specific heat of the material. M is what? Volume into the density. If the volume of material is more, volume of the construction material is more, in other words, if thickness is more, okay, so the response will be like this. If thickness is less, what will happen? If thickness is less, the response will be like it. The same signal will be there here. Okay, for example, if you have a metal plate separating, okay, if the signal, if the temperature is entering like this, it will come out almost like that. So that means the heat capacity, that is a product of m into cp, it plays an important role in the building systems. Okay, so also the transmitted radiation and the heat generated inside the buildings. So all these things, okay, so put together, it will try to raise the affect the temperature inside the building. Okay, and how this heat transfer, basic heat transfer, I have taken from the books. Okay, so it will be very interesting, these things. So that's why I'm mentioning about this. So initially, we can consider that at this steady state, throughout the temperature is same, but mostly it may not be like that. Okay, a small difference in temperature will be there, but we are assuming that at hour zero, okay, so I have a steady state in the wall. So this is inside surface of the wall, this is outside surface of the wall, and outside surface of the wall, because of the solar radiation, the ambient temperature will increase, and the solar radiation also will be increasing. So because of that, this side we have seen the transient process. So I told it will be flat, and next time step it will be going like this, next time step it will be going like this. So that is how it is going. Okay, so some morning it is here like this, afternoon, okay, so the temperature is peak, outdoor temperature is peak, so I have it like this. Okay, indoor temperature, if it is conditioned, it will be maintained the same. Okay, and after that, what is happening? So I will consider that this is a east wall. Okay, consider that this is a east wall. So now after that, what happens? So the radiation is cut off. Okay, from the east wall. So what happens? Only ambient temperature will be there. Ambient temperature will be at a high temperature, but the radiation is cut off. So because of that, there will be a dip. Okay, and around the afternoon, or afternoon in the evening, so you will find that the ambient temperature will be going down, radiation also will be going down. So because of that, there will be a very good dip here. but this peak is moving inside, that you can see. Okay, and night time you can see the temperature is less outdoor, but indoor you are, what is that? Indoor the temperature is higher. So that is what we are saying. Okay, so that is what we are saying. So that is what is transience. So because of because of the wall, so we are finding that the temperature wave is moving inside. Okay, and it is but it is peak is obtained during night time, you can see. Okay, peak is obtained during night time. Daytime it is less only, but night time the peak is obtained. So that is why we say transience is very important in the wall structure. Okay, we have to study the wall structure. Okay, so this is an interesting case which we have to discuss. That's why I've taken this. Okay, and how the wall structure is affected. So if it is a small mass, that means if the thickness of the wall is lesser, okay, uh, the the amplitude will be reduction will be smaller. Okay, the shift also will be smaller. If the thickness of the wall is very much higher, the amplitude reduction is higher, and amplitude reduction is higher, and the shift is also higher. Okay, so here I can see. Okay, so here I can see I have the heat flow. Okay, so I have the heat flow. So you think that it is from outside. Okay, and so daytime it is higher, nighttime it will be lower. So it is approximated like a sine curve, but it is not so. Okay, strictly speaking, it will not be like this. Okay, so after that, what is happening? If the wall, after passing through the wall, like we have discussed here, after passing through the wall, so inside when it is coming, it is like this. Okay, so inside, outside it is like this. Outside it is like this, but inside you are having it like this. Okay, inside you are having it like this. So what is happening? The peak is getting reduced. The peak is getting reduced, and you are finding even this also it is getting reduced. The peak is getting reduced, and still you can see that. Okay, so uh, uh, if the insulation is there, okay, so here you see the B1, B is just insulation. That means amplitude is reduced. The effect of insulation in a building wall is to reduce the amplitude, but the effect of thermal mass M into Cp is to reduce the peak as well as to shift. So that means reduce the peak as well as to shift. The effect of thermal mass is to reduce the peak and then shift. Both put together, what will happen? So it will reduce the amplitude, okay, and it will shift. So that is how I will be having. So inlet outside this curve will be like this. Into the building, this will be more. Okay. So this is something interesting. You have to know. Okay. So that is why we are going for. So that is why I am saying it is transient. Okay. So in a summer condition, or in the equatorial region, okay, or in the tropic zone, so this things will be happening. So that is why when the load calculation, it is transient. Okay, so transient means it is whatever we have outside will not be having inside. Okay, but there will be a drop in the temperature. Okay, so there will be a drop in the temperature and there will be a shift. Or in other words, heat value will be reduced, and it will be a maximum will be appearing after 4 o'clock or 8 o'clock, depending on the case or depending on the thickness of the wall. So that we have to understand. And one more thing we have to note is that the radiation which is entering into the room, okay, through the glass. For example, if it is a transparent glass, okay, white glass, okay. So in the white glass, you will find that whatever outside radiation is there, directly it will be entering into the building. So the entry of the radiation into the building, it is instantaneous. That too through the flat glass, white glass, it is instantaneous. Okay, so that is an instantaneous curve. But the entry of heat through the wall, okay, it is not instantaneous. So there is a drop in the peak and there is a shift is there. So two important things you have to understand. Okay, so that means if you are, so for example, you take a car. Inside the car, you will not see this peak shift and drop, because inside the car also we are doing air conditioning. We are also calculating the load, but you will not have this shift and drop in the amplitude. Why? Because mostly we are having glass only. Okay, so heat will be entering immediately into the car cabin. So that means what? It is instantaneous. So that means whatever this thing is there, this signal is there, that directly it will be entering. So that is what we have to understand. So if you are having an open glass, okay, white glass, there the entry into the building will be instantaneous. Okay, But if you are having the tinted glass or the glass with insulations, double pan and other things, then you will have the insulation as well as the shift that is possible. So very important thing, this concept you should understand. Okay, the glass, for glass the entry will be immediate. Similarly, if you are taking outdoor air, okay, so that will be immediate, because you will be at that point of time, what is the outdoor temperature, that you will take it immediately. Okay, so that means outdoor air, infiltrated air, outdoor whatever outdoor air is there, it will enter immediately. Similarly, radiation. Okay, radiation through glass, it is instantaneous, it will enter immediately. But through wall, it will not be immediate. Okay, so the peak is shifted. So that means if the heat is entering at 12 o'clock, okay, so that will be felt at 4 o'clock or 8 o'clock, depending on the thermal mass or depending on the thickness. So that is what we have to understand. So this concept I wanted to discuss today. Okay, so every day we are discussing some new concept. Today we have to discuss some new concept. So that is what we are discussing today. After that, we will move to the PCM integration in the building. And also, we have not discussed about the response function method. Okay, so we can do the modeling. I told you that the modeling can be done using the finite difference method, that is numerical method. Okay, though the results will be good, so still we have methods. Okay, so that is methods like system function methods. Okay, so that we can use it for the same calculation of heat flow inside the building. Okay, so in this system model, so you will be having input variables. So that is so what I told in the class 1. So what is simulation? It is a performance. It is a response of your system to external excitation. What are external excitation? So these are all the climatic parameters are the external excitation, and you have the system structure. That is whatever the building structure we have. So that is a system. What is the output variable? So heat entering into the building. Okay, heat temperature of the heat entering into the building, or you calculate the heat entering into the building. So all these things will be constituted. Okay, so this is the system model. And you have a different transient solution to dynamic analysis of the building. Okay, so distributed models, I have numerical methods. Okay, so I have a finite difference method. Okay, so I have a numerical method, finite difference method. Even you can work out thermal network analysis also. So there are some good books for studying this thermal network analysis. That also it can be done. Transfer function models, it can be, it is used by these solvers. Okay, so hourly analysis program, carrier, trace, DYUT, Department of Energy, Equest. Okay, so here it is used. Okay, so CLTD, CLF method are older versions. So now this is used, and finite difference method is also used. Okay, so I've shown the solver finite difference method is also used. Okay, so both options are available. Okay, so transfer function models for conduction, then heat balance method for the room response. Okay, so that is used in the energy plus. Okay, and we have a simplified approach called radiant time series method. So we are going to discuss about transfer function method and radiant time series method, because somewhere when you are studying about energy simulation, you will be coming across these two methods. So coming to for this problem, you should not tell that we don't know. Okay, so we are going to discuss these two topics also now. So first we are going to discuss about the transfer function method. Then we are going to discuss about radiant time series method. Okay, so finite difference method, it is known to us. We divide the domain into a lot of nodes, and after that we do the discretization. We do the energy balance. Okay, so these two flux will be same if it is steady state. If it is different, it will not be same. This will not be equal to 0. I have the residue, so that the residue is the heat stored inside the material. So this we have discussed. Okay, so from that we are finding out what is the time at the next time step. So you put everything on the other side, so that if I have all those things on the present time step, that is called explicit method. If I have all those things on the future time step, then it is called as implicit method. So you can take weightage between the explicit and implicit. It is called a semi-implicit method. All these things we have discussed. Okay, maybe tomorrow we can have a discussion on this also when we are going to CFD. So we can have a discussion on this also. Okay, since we have discussed, I will proceed to the next discussion. Okay, so the what is that? Okay, so the method. Okay, so the method what we are using, transfer function method. Okay, transfer function method. So we are going to use the principle of superimposition, okay, of linear systems. Okay, so using that concept, we are going to find out the conduction, okay, conduction function, okay, for the building. conduction function for the building wall. Okay, you can take a particular wall. You can do this analysis for individual walls. Okay, and after that you can add everything together. So you may ask why individual wall. So there is a reason behind that. Okay, so mostly what you will be doing in a transfer function method. So we will be first step will be we will be calculating the solar temperature. So first we have to understand what is solar temperature. Solar temperature is that we are converting all the radiations. Okay, so all the radiation which is falling on the surface of the wall or the glass into equivalent temperature. Because if you are working with the temperature and the boundary condition, so it will be easy for you for the simulation. So even for finite difference method also, if you are giving a temperature boundary condition, so that will be easy for you for the simulation. But if you are giving a if you are giving a radiation boundary condition, so then there may be some problem. Okay, so there may be some problem in the convergence. So because of that, what we will be getting mostly we will be converting the radiation into solar temperature. Okay, so what is solar temperature? Whatever the outdoor temperature is there, and whatever the outdoor radiation is there, that you will be dividing by the absorptivity to convert that into the temperature. Okay, maybe into the difference. Okay, so we will be, so that means what the all that radiation is converted into equivalent temperature, outdoor temperature plus radiation corresponding to, I mean temperature difference corresponding to radiation. So that means this value will be higher. Okay, this value will be higher. So how this value will be higher? So morning in the east, the solar temperature will be higher because the sun will be radiation will be in the east. Similarly, around 10 to evening 3 o'clock, solar temperature of the ceiling or the roof will be higher. Similarly, west after 1 o'clock, west the solar temperature will be higher. So because the solar temperature is a representative of the radiation. Okay, so you can wherever the radiation is more, the solar temperature will be more. So that means we also understand that whatever the radiation falling on the east, it need not fall on the, it will not be same as west as well as north and south. Okay, so that means already we know that sun mostly it will be falling on south, southeast, east, west or south, or east, west, north. So that is how it will be doing. So if it is, for example, you consider now you think that the condition at Chennai now, so the sun will be in the south. Okay, so that means what morning it will be rising at the east. Okay, and it will be setting at the west. So it will be traveling in the southeast. Okay, southeast. Okay, in this direction. Okay, so it will be traveling. So what happens to the north? There will not be heat transfer. Yes, definitely heat transfer will be there, but not because of radiation. That is because of the ambient temperature. So ambient temperature will be higher in the north. So because of that, the heat entry will be there. So that means what? So if you are considering this point of time, that is at November. Okay, for Chennai, the sun will be at east. Okay, rising at the east, and it will be traveling in the south direction, southeast. From southeast to southwest, it will be going. In the north, there will be no exposure. Okay, so that means what? It depends on the day. Solar temperature for solar temperature is typical for each surface. That is point number 1, and it depends on the day. Okay, it depends on the day. Okay, so because if I do the same calculation during the month of June, the exposure will be in the north for Chennai. Okay, because it will be June solstice. Okay, so the exposure will be in the north, morning east and north. So okay, now I think you have to understand. So solar temperature is typical for each surface. So that means you have to do the calculation for each surface separately. Okay, so what is the objective of doing this? We want to give the radiation input or convert that radiation input to solar temperature. We want to find out what is that response. That means what will be the effect of this radiation to the indoor, how much heat is entering indoor. So that is what we are going to calculate. We are going to use the principle of superimposition of linear systems. Okay, so what is the concept? What is the principle of superimposition of linear system? The response of a system due to several inputs acting simultaneously is equal to the sum of the response of each acting alone. Okay, so that means what? Whatever the response is there for a several inputs. Okay, so if I add the responses of the individual systems, so that then I'm going to get the total response for the system. Okay, so that is the concept. So that is what we are going to use. Okay, so from there we are going to the transfer. So that is the concept behind the transfer function model. Okay, okay, so now what is that we are interested? So we are interested in the room temperature, that is TI. Okay, TI is the room temperature or inside temperature. I can call it as inside temperature. So inside temperature is dependent on the heat input, that is from the outside, as well as the outdoor air temperature. So the heat entering into a building, it is dependent on the heat entry, that is the radiation heat which is entering inside the building, as well as the outdoor air temperature. Okay, so as well as the outdoor air temperature, as well as the outdoor air temperature. So now what I am doing, so I am writing the all the indoor temperatures. Okay, indoor temperature series I am writing. Okay, so that means what temperature at the first hour, temperature at the second hour, temperature at the third hour, like that dot temperature at the 24 hours. Okay, so I put it together. Then what I am doing, I am taking all the outdoor temperature. What is the outdoor temperature? Outdoor temperature is the the temperatures which are calculated. Okay, all for 24 hours. You know the outdoor temperature for all the 24 hours. Okay, so you calculate that. So you have 24 temperatures, outdoor temperature, 24 indoor temperatures, 24 outdoor temperatures, and then I have 24 heat inputs. Okay, so I have 24 heat inputs. Okay, so I have, okay, so if I take this together, okay, so if I take this together, so now I can so that means I should have 24 data. I'm sorry, 24 data, and I should have 24 coefficients. That means each of this I should have 24 coefficients. Okay, and okay, so that means that's what for three sets: for indoor temperature 24 coefficients, 24 temperature; for outdoor temperature 24 coefficient, 24 temperature. Similarly, for outdoor heat input, 24 coefficients and 24 temperature. Okay. Now, from this, you can calculate whatever you want, the temperature you want. Okay, at any instant. Okay, you can calculate it. So that is the principle of superimposition. So I am taking all these values. I am taking all these values. I am taking all these values. Okay, and I can have all the 24 coefficients. Okay, for I can take it for calculation, or I can reduce the numbers also. So here what we are doing is just we are reducing it to 3 only in this problem, or in this method what we are discussing. Okay, so these coefficients are reduced to 3, and that means it is sufficient to have 3 indoor temperatures at 3 time intervals. For example, indoor temperature at 1 night 1 o'clock, indoor temperature at night 2 o'clock, indoor temperature at night 3 o'clock. Similarly, outdoor temperature at night 1 o'clock, night 2 o'clock, night 3 o'clock. Similarly, heat input at night 1 o'clock, night 2 o'clock, night 0 o'clock. You know that will be 0. Okay, so that is what we are doing. So similarly, when I am going to the next calculation, so what I will do now, I will leave the 1, so I will go 2, 3, 4. Okay, and you will go to all the coefficients. Okay, so similarly, I am going for the next calculation. So then 3, 4, 5. Okay, so like this. So then how to find the coefficients? Okay, so you know all the values. Okay, so you know all the values. So that is 24 indoor temperatures, you know, 24 outdoor temperatures, you know, 24 heat inputs, you know. Okay, so that means you can find out how many coefficients are there. Okay, so you can find out all these coefficients. You can give all the data, and you can find out all these coefficients. Okay, by equating the coefficients. Okay, so for example, it is AI naught. You can find out. Okay, similarly A1. So similarly A2. So like that, all the 24 coefficients you can find out. Okay, and after that finding out, so now it is like this. Okay, so you have the conduction heat. So this is in the next time step. Okay, so this is conduction heat at the present time step. So actually it should be here only. This should be here. The summation of that is what for the step whatever you are calculating, it is there here. The balance all the step where it is, so it is there inside. For example, if you are having 24 coefficients, all the 23 heat inputs for different times, it will be there here. But here I told you will be using 3 coefficients. Okay, so that means 3 values will be there. Similarly, here also 3 values and 3 coefficients will be there. Here also 3 values, 3 coefficients will be there. Okay, and area also you have to multiply. So that is very important. Okay, so because the heat input, it is dependent on the area. So that factor we are bringing it here. Okay, so that factor we are bringing it here. It is like a UA del T. Okay, it is like UA del T. So that is what we are trying to get it. So when you are equating to steady state, then you will understand. So now what you have to understand is this summation. Okay, so this is full heat. We put it in one place, and solar temperature we are putting into one place, and indoor temperature we are closing one place. So in the previous case, I just told it is outdoor. Now I'm telling you solar temperature, indoor temperature, and heat you are calculating. Okay. So based on the data, so we will be doing the calculation. Okay. So it will be very interesting. Okay. Now what is that? So if the transfer function, it will be subjected to physical constraint under steady state limit. So because if I sum everything, okay, so if I sum everything, it should the value should be equal to the steady state value. Okay, so that means d naught. Okay, so this is the method. Okay, so this is the method. Okay, strictly speaking, you have to do all the 24. Okay, but if you are able to get the correct values, you can stop. You can stop with 4 or 5 also. Okay, so in this example, they are using three numbers. Okay, so now I'm taking since the limit we also have conduction. So what is the conduction value? Okay, so the conduction value is the UA solar temperature minus Ti. So that we know this is steady state heat that is transferred inside the body. Okay, so at the steady state this will be the system. So if this is the system, so what is the meaning? The meaning is that this and this should be equal, then only this can be formed. Okay, if these two are equal only, then you can take it outside. Okay, and if these two are equal and if you take it outside, that will become U. Okay, so what is U? U is summation of C divided by summation of D. Okay, so at this steady state. Okay, so at the steady state, so these two values will be equal. These two values will be equal. Okay, from that I am calculating Q is equal to UA del T. So these are equal. I am putting it outside. Either you can convert this into summation B or you can convert it as summation C. This I am taking it outside, and I am having summation D here. Okay, so what is U? It is obvious. Here they have taken at summation Cn. Okay, or even it is as good as the summation Bn also, because both are equal. So that divided by Dn. So at the steady state, you are taking this outside, and you are making Q is equal to UA del T. So U, from that you are deriving that U is equal to summation of C divided by summation. Okay. So how many numbers of calculations you are making? So many numbers you can take it. Okay. Here we are going to see an example. Okay. Here we are going to see an example with the 3. Here you can see, and it is interesting to note that the transfer coefficient values are given in the data book itself. It's not in the data book created by the foreign authors. Okay, so we have these values of conduction transfer coefficients. Okay, for standard walls they have created. Okay, so that's for standard walls. For roof, so if you take roof, so they have the values. Okay, so what is the B? So B naught, this is B naught, B1, B2, B3, B4. So D naught, D1, D2, D3. Okay, and the summation of Cn, it is given totally put together. It is given here. Okay, and if you based on this, okay, if you calculate, okay, based on this, so how you will calculate? So you have to go to this equation. So this is the equation where you have to solve. So that means for the 3 steps, you have to calculate what is the solar temperature. 3 times you have to calculate what is solar temperature. Similarly, indoor temperature. Summation of B, just now we have seen in the data book. Summation of Cn, totally it is given in the data book. A, it is area of the cross section of wall. Summation of Q, in the first time step, when T is equal to 0, Q will not be there. Okay, first you have to calculate from that only. So that means the next time step only you will be getting these things. Okay, so initially we will take it as 0. Okay, so it is an iterative method. You will not just take it from one iteration and give the answer. We will go for 2, 3, 4 iterations. It is clearly given this, so that's why I have taken this. Okay, so this is how we will be having the B naught, B1, B2, B3, B4, D naught, D1, D2, D3. Okay, summation of Cn. Just now I told you. So that means all the things are all the values are there. Just what you have to do, that Q what you want to find out at 0, that only you have to calculate. All the other things are given, and previous data also it is there. Solar temperature data is there, indoor temperature data is there. Q is not there. You are going to calculate that. Okay. So if you are going to calculate the U value is going to be this much, and the time lag is going to be 2.43 hours, and the lambda it is 0.94. Okay, lambda is going to be 0.94. Lambda is 0.94. Okay, fine. So this is a decrement. This is a decrement. Okay. So like that, they are given for various layers of roof, layers of wall. So these are all samples. If you go to the standard data book, all these things will be there. So I think researchers they have worked out and they have found out all these values. So it is ready. So it is just you have to pick up and put the value and then you have to solve it. Okay. Okay. So now similarly, the thickness, thermal conductivity, all these parameters we have to give it in the problem, so that you can give it. Okay. So that you can give it. Okay. So you can give it and you can get it. Now there is a sample problem it is given. Okay, so here it is given TA is 25 degrees centigrade inside a set temperature, that is AC air conditioned. Okay, solar temperatures you have to calculate. Okay, so you have to calculate, and this values they have taken from the data book. Just now we have seen the data book. No, from that they have taken this data book. So first step conduction at time step 1. Okay, so it is calculated. And initially we will be giving it. So the values you take it D1, you take it on the table. But what is Q? 0. D2 taking data book. What is the value? 0. So on B0. Okay, so we are taking. And what is the solar temperature at time 1? So that it can be calculated. Solar temperature at 1 it can be calculated easily. Similarly, solar temperature at next time step. Sorry, this is solar temperature at 0. Solar temperature at 1 and solar temperature at 2. Okay, and solar temperature 3. So that means 4 values they are using. Okay, 4 values they are using. Okay, since here you are having 4 coefficients, we are using 4 values here. Okay, and then TA into CM. So the TA is the indoor temperature. So it is common for all the things. Okay, indoor temperature it is going to be common, but the solar temperature it is not common. Okay, so it will be different at different hours. Okay, indoor temperature will be same on different hours. Just we are putting summation of Cn. Okay, then we are calculating what is D0, D1, D2 and D3. Okay, so we are calculating D0, so D1, D2 and D3. Okay, so I am doing all these values. Okay, I'm doing all these calculations. Okay, I'm doing all these calculations, and when I sum that, I am having a 0.020. Okay, when I sum that. Okay, I have 0.020. So this is the value. So that is the heat conduction heat conducted at 0. Now what is that next step? What I have to do? So this value when I do for Q D2 Q of 1 Q conduction of 1 2. So that means this will be there inside. There I have to substitute. Okay, so that means it is like for 1 you calculate, then you go second to put 1 value. Similarly 2 you calculate. When you go to 3, you put 1 and 2 value. Then 4 you calculate. So now 3 values are there. Substitute it. So next like that you proceed. So that means you have to every hour you have to do the calculation. Okay, so it is interesting. You can see it. That is given in this table. It's very interesting. Okay, so now you can have this time. Okay, so this is the time. Okay, so initially they are taking before hours. So that means they are this is like my night 1 o'clock. So they are taking the 3 values before that, because we will be interested in from 1 o'clock. So if you want from 1, that means you have to take before 3 values. So they are doing some dummy -2, -1, 0. They are doing it at dummy. Okay, so that is what. So this is 12 o'clock. This is 11 o'clock. This is at 10 o'clock. Okay, so they are doing this dummy calculation. After that, the real calculation starts. So that means when I use this value, okay, solar temperature value, I use these 3 values, I am getting this one. Okay, so then I use these 4 values. I think in this it is 4 values. So I use these 4 values, 3 values, I get this one. I use these 4 values, I get this one. Okay. Similarly, next 4 values, I get this one. So like that, I am calculating. Okay. So all the values I am calculating. I'm filling the table here. Okay. So what is that? This is the Q conduction. Okay, first iteration. By seeing that, you will think that this is correct. This is not correct. Why I am saying this is not correct? Because when I am starting some simulation, okay, this is also very important thing. You should understand. This is very important thing when you are going for building and simulation. When you are starting at night at 12 o'clock this day, so whatever the conditions that were there today, if it is a clear, non-rainy, non-cloudy day, so whatever the Q value I have it for this year. For example, today night 12 o'clock or 1 o'clock. So same thing after simulation, the next day also I should get the same value. So then only my simulation is correct. So for that checking, here you can see 1 o'clock, what is the value? It's 0.020. So what is the 24th hour? What is this value? 10.246. You know that suddenly from 0.020, it cannot go to from 10.246. Suddenly it cannot go to 0.020. That means there is some problem. So what I have to do? I have to go for one more simulation. That means one more calculations I have to do it. So now I am taking that it is for the next day. I am taking it as the next day, but really I'm calculating for the same day only, same input only I'm doing, but I am doing the calculation again. Okay, and here only that concept is coming. So warming up days, they call it as warming up days. So that warming up days. So when you do this calculation, automatically this warming up days, it will come into this simulation. Let us see. So now I'm taking these three values. Okay, I'm taking these three values. Okay, these three values, and I'm putting it here. I'm starting the first calculation. Okay, okay, fine. So I'm doing the same, repeating the calculations here, and after this, I'm taking these three calculations. Okay, I'm taking these three calculations. I'm putting it here. Now let us check for 1 o'clock. What is the value? 9.631. And 24, it is 10.860. This is almost near, but still both should be equal. So next we will go for the next simulation. Okay, so I'm calculating for 72 hours. So I'm using these three values here. I'm calculating the next value. So I repeat it here. So now again I'm checking, and 24th hour, what is that? 10.861, and 1 o'clock it is 9.661. Okay. Okay, so now you can see the dummy 24th hour is 10.86. Here the dummy 10th hour is 10.861. Okay, so that means I'm doing it for once again. Okay, now here you can see whatever the dummy hours you are taken here. Now it is almost the same, 10.862. That is acceptable. So that depends on you. If you are accepting that, then it's acceptable. Now what is happening? So it is like you are starting the simulation without anything. Okay, so that means here the values are not it is not periodic. Periodic means it should start from the some value and it should end up with the same value. For example, night you take the ambient temperature itself. So if the night temperature is around 25 degrees, the next day also same time it should be 25 degrees if there is no major disturbance. So that means that is correct. Similarly, the heat entry into the building also, if today 1 o'clock if it is some value 25 kilowatt, so the next day also it should be 25 kilowatt. So that means your thing is correct. That is how we find out. Okay, so whenever we are seeing some journal papers and everything, so we will find out whether these two things are matching. If these two are not matching, we will say that the simulation has not been done properly. So we'll tell the researcher that the simulation has not done. So this has been incorporated in the software as the warming up days. Okay, so here you can see how many warming up days it is taking. So it is 1, 2, sorry, 1, 2, 3, 4. 4 warming up days it is taking. So after that we are finding it. Okay, so it is possible somebody new to the simulation, especially when we are writing their own code. So this problem will be there. Okay, so they may be calling this as the solution. Okay, that's correct, but it is not. It is correct as per calculation, but it is but general logic it will not be matched. So that is why we are going for warming up days. So this is the conduction transfer model. Okay, so using the conduction transfer model, I do the calculation. Okay, So this is the solar temperature which I am calculating. This is for a particular wall. Again, I am telling whatever the problem we have solved, it is for a single wall. East wall means east wall alone. Yeah. So similar calculation you have to do it for west wall. Similarly, you have to do it for roof. So like that it should go. So here, as per the calculation, this is the solar temperature. That means it is a representative of radiation. Okay, outside the building or outside the wall. And what is happening to the solution? Okay, so first we are starting with the iteration. Red color, it is the first iteration. So like this one. Okay, and uh, so okay, I'm sorry. So the red color, so this is like this. Here it is shown. Okay. Now what is the problem with this red color? This red color, you are finding that here you can see it is at 50 degrees centigrade here. Okay. And what is this temperature? I'm sorry. So it is 50 watt per meter square. What is the heat here? It is 0 watt per meter square. So usually when you are not taking the warming up days, it will be like this one. So it will start from 0 and it will end up with this value. So now what you have to do, if you are going for warming up days, what happens? So this value will be, it is increasing. Now you are seeing with the iteration, you are seeing that this is reaching 10 watt per meter square. And here also it is reaching 10 watt per meter square. So then that is correct. And similarly temperature also, if you do in the temperature scale, here you can see this is 50 and here it is 15, not correct. So here you can see this is around 52 or 50, you can say it is 50, and here also it is almost 51. So temperature is also same and heat value is also same at both of these. So that is correct. Okay. Okay, so using this you can compare the various, so like how you are doing in the energy simulation software. So in the energy simulation software, the calculations can be done by this or finite difference methodology. So here that is how it is given. So two things are they are comparing. Okay, so they are comparing the solar. This is the input. Solar temperature is the input. You may be knowing, and if it is a steel sliding, so that means it is a steel door. It is like a steel plate. So I told you the transients will be smaller. Okay, it will enter immediately. So just a fraction of 1 hour it is entering into the building. But if it is a 300 mm HW concrete, what is happening? The temperature signal itself is not there. You can see. Is the temperature signal is there? No, it is not there. Okay. So that is what. So this is very interesting. Okay. So this will be very interesting. Okay. So I told you we have studied about the finite difference method. So this is the next method. It is a transient. It is a function. Okay. Wall response function method. Okay. Okay. So we are going to the conduction response function method. We have seen that. Next we are going to the next method. So it is called as the conduction time series method. Okay. So conduction time series method you can apply it for 1D problem. Okay. And one more thing, for the reference for this conduction response function method and the conduction time series method. So you can refer the book by McQuiston and Parker. Okay, McQuiston and Parker. You can refer the book by McQuiston and Parker. So it's a very good book. So a detailed discussion is given there. Okay. So you can you are taking 1D heat flow for a opaque building. So we are going for RTS, that is a radiation transfer method. So conduction transfer method okay. So we will be involving both. We will be using the transfer function model. Okay, but here you will be using time series model with the lagged values. Okay. So the conduction transfer function is to use iterative method. So we start with some value. Okay, we do some like a warming period. So we do the calculation. So finally we get so what is the meaning of warming period? Actually, it is iterating to the correct value. Okay. So likewise in the conduction transfer in the conduction time series method, radiation time series method, it is also called as radiation time series method. So we will not be iterating. We will be directly calculating the value. Okay. We will be directly calculating the value. Okay. So what is the procedure? What is the procedure for radiation time series method? So we will be calculating the solar intensities for each hour from the exterior of the surface. We will be calculating the solar radiation. So after that, we will be calculating the solar temperature for the exterior surface for each hour. Okay, we will be calculating the solar temperature for the exterior surface for each hour. Okay, and the solar radiation we will be giving as input to the solar, that is glass. Okay, windows, glass windows, okay, so which will be directly enter into the building. So that we are doing. And then solar temperature we are giving it as giving to the exterior surface, that is wall surface, and we are going to the heat gain for windows for each hour, and we are depending lighting, occupants, and everything for each hour. So don't think that internal heat gains will not contribute for temperature rise. Yes, that also will be contributing for the temperature rise. That will be inside the building. Okay, it will be inside the building. It is instantaneous. Okay, unless or otherwise if radiations are undergoing multiple reflection. Okay, so then there will be transits. Okay, so again infiltration will be entering into the building. So all these things we are in. So all the heats we are taking, we are clubbing. Okay, all the heats we are taking. Okay, so that is from through the glass, through the walls, okay, through the windows, okay, through the lightings and everything we are taking. Then what we are doing, we are segregating. Okay, segregate. This is very important. We are segregating the radiative component and convective component. Convective component directly we are adding to the hourly load in the each hour. Okay, the radiative components what we are doing, we are putting it in the time series method. Okay, so the radiative components we are putting it in the time series method. Okay, so we are calculating the hourly cooling load. Okay, so to the due to the radiative heat gains. Okay, so I have the CTS model. Okay, so in the CTS model, what is happening? Convection, it will be separate. Okay, so we are this is the flow chart. Okay, so all the components we are doing. Okay, so we are splitting into radiative and the convective components. Convective components directly we are adding to the corresponding hour. Radiative components we are not adding to the corresponding hour. We are adding to the next one. Okay, we are adding to the we are like the time shift and all we are applying for the radiative components. Okay, like just now we have seen no, the shift and the peak reduction and the shift in timing. So we are applying for the radiative components. Okay, that we are not iterating. We are going for calculation. Okay, we are going for direct calculation. Okay, so now I have conduction. Okay, so I have the conduction component. Okay, so conductive component. So which is what I am calculating. So this is UA into these are called as the radiation time series factors. Radiation time series factors. Okay, number of factors will be there, and it is be given in the data. Okay, so for the specific thing you can calculate it from the data book. Okay, and how we are calculating. Okay, so all the loads will be taking, like you will be segregating all the convection coefficients, that will be separated, and for each time step we will be calculating the radiative component. So for radiative component there will be a shift, and there will be a reduction, so that we are calculating. How we are calculating? So this formula only we are using. This is the formula for first one, hour 1, hour 2, hour 3, hour 4, hour 5. So like that we will be taking. For each hour you will be having the solar gain. Okay, so I have this value. So I have the temperature difference. I have another temperature difference. Next temperature difference. So I have the values. Okay, so UA. So I have the values. Okay, so I have the values. So when I sum it together, okay, so I get the 14.2, 14.02. Okay, so I have UA, and then these are the factors. These are the factors. This should be taken from the data book. Okay, these are the radiation factors. Okay, and these are the temperature, solar temperature. How many temperatures? All the 24 temperatures you put, and all will be having 24 radiation factors. So when I calculate QA, I'll be getting the correct value. Similarly, if I do it for 2, I'll be getting the correct value. So like this. Okay, so we'll be calculating for all the 24 hours, and you will be getting the shift. Okay, so we'll be getting the graph. Okay, so this is the factor, and this is the solar temperature, and this is the heat what we are calculating. So you can find the solar temperature is peak in this region. The peak of the solar is okay, so somewhere here. Okay, so the solar temperature peak is somewhere here, and okay, and there is a small shift. Okay, there is a 3-hour shift is there. So here you can see 75 is the maximum solar temperature, but the heat input, it is maximum at 24.48. So that is there. Okay, and all this solar temperature difference, if you club it together, okay, so that is total del T, that del T minus 25. Okay, So multiplied by U value, I should get 8.71. So that is the summation. Okay, so that is the heat input, okay, into the building. This is steady state heat entry. Okay, this is equivalent to steady state heat entry. So now this is a radiation time series method. Okay, you can use two methods. Okay, so in the solvers, I have told you, so that the conduction transfer function method only it is used, and in energy plus they are using a radiation transfer method also. Okay, this method is given by McQuiston. Okay, so who wrote that book? Okay, so he has given. Okay, and it is there in the Ashray journal also. Okay. Okay, so now that we have studied some two new concepts, okay, for load calculation, so it is something different. It is not like your finite difference method. Finite difference method is something different, and this is like exact method. We'll be going for calculation. Okay. Okay, so now for a wall I have taken, and I'm calculating using the conduction time series method or radiation time series method. So I'm finding the shift. Okay, so I'm finding the shift. Okay. For light wall and heavy wall, I'm finding the shift. Okay. Okay. Now we will go for our discussion, today's discussion. So that is the PCM integration in building. Okay. So why I was discussing about these things, because if I talk about the PCM integration building without this discussions, you will not understand. So that is why I've gone for this PCM integration in buildings. Okay. So in a PCM integration, why we are integrating PCM in the building? Okay. So you know that the materials which are having a high storage values, like concrete or pebbles and other materials. So the M into Cp of these materials, or the Cp of this material will be higher. So naturally, if heat capacity is more, so you know there will be the drop in the temperature, and there will be shift will be there. Okay. So if you are taking concrete material or other wall materials, so if you want to reduce this peak and shift it, okay, so you require a very big wall. Okay, you have to construct a very big wall, so that only you can reduce the heat entry into the building and shift it. But what a phase change material will do? So in the phase change materials, you will be putting the slabs like this here. The phase change material will be having a very high Cp value. So literally speaking, it will be having a very high Cp value, because, but it is very important, it will be having a very high Cp value only for a specific temperature range. So that specific temperature range, it is called as melting range. So we have a solidus temperature and we have a liquidus temperature. Liquidus temperature is a high temperature, and solidus temperature is the lowest temperature. Okay, liquid, or you can take it like this. Phase change material, as the name indicates, it's a material which will be changing its phase. So in the process of changing its phase, it will be absorbing and releasing the heat. So you take the phase change material, you start applying heat. Okay, so first it will be in the solid state if it is at a lower temperature. So you start applying heat, it will be converted into liquid state. Okay, so when it is changing its phase from the solid to liquid, in that two-phase region, it will be absorbing more amount of heat. So the other way of telling that is, in that two-phase region, that is between the solidus temperature and the liquidus temperature. Okay, so it will be absorbing more amount of heat. In other words, technically we can say that the Cp value of the phase change material will be higher in this region. Okay, like how the Cp value of pebble, okay, even water also it is higher. Okay, so even concrete and other materials. So Cp value, if it is higher, it is shifting the material. Okay, it is shifting the peak. Okay, it is reducing the peak and it is shifting the time lag. Okay, because of time lag, it is shifting the heat. So the same thing a PCM can do it. But if you are going for construction, so you have to go for a very big construction. But if you are going for a phase change material, a small slab of phase change material, it will be equivalent to a very big wall. So that is what we have to understand. Okay, so that is PCM or phase change materials. So nowadays, phase change materials, it is applied in the buildings. Okay, for this purpose. So it is applied in cold climate. Okay, for increasing the heat capacity in the building, so that the heat will not be entering into the building. Okay, in the conduction form. Okay, so now you can see this is how the PCM slabs will be given in the body of the building. And so here, this is the thing. Okay, so this is the temperature. This is the phase change temperature. The phase change temperature, it can be a constant temperature for a crystalline substances. Inorganic PCMs will be like this. If you are going for organic phase change materials, so it will be having a range of phase change. So this will be one phase change temperature, and this will be the another phase change. So this temperature, this is the solidus temperature. This will be the liquidus temperature. So in this region, okay, so in this region only it will be absorbing the heat. Okay, so if I put the phase change material in the body of the building envelope, so it will be absorbing the heat. Okay, so it will be not allow the heat to enter into the building. Okay, or it will reduce the peak of the heat entering peak, and it will be shifting the peak when it is when the heat is entering into the building. So that is how if I am having a if the external temperature is like this, okay, external temperature on the wall it is like this, and internal temperature is supposed to be like this. If I am integrating, okay, so if I am integrating the PCM, okay, what is happening? You are finding that the indoor temperature is reduced. So what is that you are happening? Well, you seeing, so you are seeing that this is external, this is internal. The peak is getting shifted and amplitude is getting reduced. From afternoon it is going towards evening, and amplitude of heat entering the building it is reduced. So whatever a job a very big thick wall or a high capacity wall, high volume wall has to do, a small thickness of PCM will be doing that because of high specific heat in the phase change region. Okay, so now how you can go for modeling of phase change in a building? Okay, so I can go by enthalpy porosity model, or I can go by apparent heat capacity model. Okay, so in the enthalpy porosity model, okay, so it will be it is mostly used in the CFD solver. Okay, so here what we will be using is you will be having the energy equation, whatever the equation that is the temperature or enthalpy equation what we have. So here we will not be solving that for the temperature. Okay, so you will be having the liquid fraction. So from the liquid fraction or from the temperature itself, we will be identifying whether it is in the phase change or it is in the solid state. For example, if you have a solidus temperature and you have a liquidus temperature. Just excuse me, only 1 minute. So here you can see. Okay, so here you can see this is the temperature axis and this is the time axis. Okay, so now this is the temperature time diagram for a material with the range of phase change material, mostly organic phase change materials. So that means in the solid range the Cp is constant, okay, and the liquid range the Cp is Cpl. And here you can see that this is the Cp value. Okay, so here it is so that is in this range only it will be absorbing the heat. Okay, so that means between solidus and liquidus temperature only it will be absorbing the heat. So now if the temperature is somewhere here, for example, you think that the solidus temperature is 30 degrees and liquidus temperature is 32 degrees. You may be wondering how it is possible. Yes, it is possible. There are phase change materials are the low temperature or they will be melting and solidifying at low temperature. There are material available which will be changing its phase at 25 degrees centigrade also and 30 degrees centigrade. Wide temperature range it is possible. Okay, suppose if this is 30 degrees and if this is 32 degrees, suppose if the temperature of 30.1 if it is reached, so then you can understand that it has entered the two phase region. Suppose if the temperature is 31, so that means if it is a half solid PCM and half liquid PCM. If the temperature has reached 32 degrees centigrade, so that means fully it is converted into liquid. So that is how you have to identify. So that means by tracking the temperature, you can find out what will be the melt fraction or the solidification fraction. Okay, so that is very important. Okay, and so that is how you will be identifying which liquid fraction. So the liquid fraction will be identified using the temperature. Okay, so that is the speciality of the enthalpy porosity method, which make the discussion simple. So the two phase region it is also called as mushy zone. Okay, so the porosity will be decreasing from 1 to 0. So what is the meaning of porosity decreasing from 1 to 0 when material is solidifying? Because when porosity is 1, there will be flow will be there. Okay, but if porosity is 0, so totally the flow will be blocked. So that means the non-movement of the PCM it will be taken care by the porosity. Okay, and yeah, so the velocity also will be dropping to 0 when the material is solidifying. So all these things are given in this material itself. Okay, and this is the energy equation. So this equation is very familiar for you. So this is a transient equation, this is convection equation, and it is a diffusion equation, and this is the source term. So this equation will be used for a three-dimensional problem. But for our case, we are in all our simulation we are taking 1D only. So that means this will be dou rho h by dou t. This will be dou by dou x of rho u v is equal to dou by dou x of co k dou t by dou x that plus sp. Okay, and when if it is in the liquid state, okay, so then we will have convection. If it is in the solid state, this will become zero. Convection will not be there. So mostly for our discussions, we will be taking the transient and the diffusion term and the source term alone. Okay, so one dimensional. We will not be taking the convection. Okay, and how we will be giving the enthalpy. So the enthalpy of the material, it is enthalpy plus the latent heat, whatever we will be giving. Okay, so h is given by the h reference. Okay, whatever zero reference we are taking, above that what is the value, plus what is the integral of Cp into dt. Okay, so we will go and we will have a discussion, a detailed discussion. Okay, so if the material, if it is at a constant, if it is so here this is Qt curve, this is Qt curve, this is heat transfer, and this is the temperature. So when I am increasing the temperature, it is changing its phase at Ts. So this is solidus temperature. So up to that, below this temperature, it is solid, and after that it will be changing its phase. Here fully it will be in the liquid region. Okay, this is liquid region, this is solid region. So this is two-phase region. So it is going from solidus temperature to liquidus temperature. Okay, so how will you find out the liquid fraction? Okay, so the liquid fraction, it is found out by T minus T solidus divided by T solidus minus 2 liquidus. Okay, T minus T solidus divided by T liquidus minus T solidus, because liquidus will be higher, because liquidus means that will be higher temperature. Okay, so this is how we will be finding out the liquid fraction. Just now I told you. So this is maximum limit, this is a minimum limit for the phase change, and T is the value. Okay, for example, I told this is 32, this is 30. Suppose if it is in 31, what is the meaning? 31 minus 30 divided by 32 minus 30. So it is 1 by 2. So then liquid fraction is half. So that is how we will be identifying the liquid fraction. Okay. So we know that if T is less than liquid solidus, beta is equal to 0. That means there is no liquid fraction. Below this, there is no liquid fraction. Okay. And if T is 2 liquidus is less than T. Okay, so if T liquidus is less than T, okay, if T is greater than T liquidus, I think there is a small problem here, I'm sorry. So if T is greater than T liquidus, okay, so then beta is equal to 1. So that means after that it is beta is equal to 1. The final case is T is equal to T liquidus, then also beta can be equal to 1, because here you can see if T is equal to T liquidus, this will become 1. So that means if it is greater than or equal to 2 liquidus, then I will have beta will be equal to 1. Okay. Okay. So now how you can include the okay, this is how the simulation is being carried out. How these values can be included in the latent heat can be included in enthalpy, because that is the main thing what we will be worried. How the latent heat can be included in enthalpy. So that we have to see. So various scientists, they have given various formulae for including this latent heat. So mostly it goes with this. Okay, so H, okay, so I have a mean temperature below that. Okay, so you can 1 minute. So here we will go back here. So here I consider this is a mean temperature. Tm, this is epsilon value. Tm minus epsilon means it is a solidus temperature. Tm plus epsilon is liquidus temperature. So that is what it is given that here. So nothing to worry. So this is Tm minus epsilon. It is solidus temperature. Tm plus epsilon liquidus temperature. So in this range, so enthalpy is function of Cp into Tp. So that's how they are taking. And the next method is if Cp H1 is Cp solid into Tp plus lambda. Lambda is the latent heat. Then what they are doing, Tp minus of Tmp plus epsilon divided by 2 epsilon. What is 2 epsilon? So again we will go back to this. This is 2 epsilon is the TL minus Ts. phase change temperature range. 2 epsilon is a phase change temperature range. Okay, and if it is Tp minus T epsilon, okay, so that means it is somewhere here only. Okay, okay. So here also, if it is epsilon minus Tmp divided by 2 epsilon, then also it represents the melt fraction. So otherwise here also Tp minus Tmp plus epsilon divided by 2 epsilon. This also represents a liquid fraction. Okay, the liquid fraction multiplied by lambda, that will be the enthalpy value. Correct? Because if somewhere in between at 50%, okay, so just now I told you, if the temperature is 31, okay, so it is 50%. So that at that point, what I will be having? So I will be having Tp 31 minus Tmp, that is 1. Okay, so Tmp is what? It will be 31. That is the middle of the value. So please try to understand. So the solidus temperature is 30, liquidus temperature is 32. So if I take somewhere in between, what is the Tp value? Tp value is 31. Okay, 31 minus again melting. What will be the middle point? Middle point after this. Okay, so the middle point is again it is 31. So it is 31 minus 31. Okay, see from the same expression we will be getting the same value. See, and Tp minus Tmp. So both are same, 31 minus 31. Again, epsilon is 1 divided by 2 epsilon. So our epsilon and epsilon will cancel. It is half. So if the temperature is 31, it is half only. So that is how this formula will be satisfying. So what is that? It is H1 plus Cps into Tp plus whatever the liquid fraction multiplied by latent heat. Here also it is same. So here and this person, okay, so this person, he has introduced one more interesting method. So he has introduced Cp effective. Okay, so like apparent heat capacity. Okay, he has introduced effective heat capacity. Okay, so that he is finding out the effective heat capacity by converting the latent heat. Okay, latent heat into a specific heat. How it is done? Divide the latent heat by the temperature range. Okay, just put this one alone in your mind. This is very, very important. How it can be included, because in design builder or any simulation software, if you want to include the phase change integration, okay, so the concept is latent heat divided by the temperature range, it will give the specific heat. Okay, latent heat divided by this is very important. Latent heat divided by the temperature range, it will give the specific heat. So that you can put it, okay, and then you can do the simulation. So that is apparent heat capacity method. So many methods are there. So there is one more interesting method of solving enthalpy schemes. So in the enthalpy schemes, if I am taking the source, if I am taking the source as some particular value, okay, or this is the source, that is the melt fraction. We are removing the energy. Okay, we are removing the energy in the system in prorata to the melting rate and latent heat. So what is happening? As the melting starts, the energy will be removed from this system. Okay, what is that effect on the system? If something is removed before in the sensible region, the temperature rise will be gradual. Okay, so again in the liquid phase, the temperature rise will be gradual. But when it comes to the phase change, when this coming into that, what will happen? This minus latent heat into dG by dt. As the liquid fraction is increasing, so the effect of that will be to hold this equation. That means it will hold this equation from solving. That means it will not make the equation to solve gradually. It will make the solution of this equation slow. So in effect, what will happen? So whatever it is supposed to happen, that will happen. So what is that? So here you can see, whenever here the solution is gradual. In the solid range, the solution is gradual. In the liquid range, the solution is gradual. When it comes to this range, so it should be slower. So how it is becoming slower? So it is being done by this source term. So this source term, when it makes its presence here, so this will stop the solution. That means it will slow down this equation. Okay, so that is how you will find the slope in that region will be lesser compared to sensible regions. So whatever you want, that is happening. In the sensible region, the rise is more, and in the latent region, the rise is smaller. So how it is affected? Not by the apparent heat capacity, it is by the source term. So that is why it is called as source based enthalpy schemes. The source based enthalpy schemes, it is applied in the commercial CFD solvers like fluent, ANSYS fluent, and other type of solvers. This method is applied. Okay. And next is apparent heat capacity method. So in the apparent heat capacity method, so we'll be solving the same energy equation. Okay, we'll be solving the same energy equation, but we'll be going for a specific heat, which is called as apparent specific heat. So how I have to calculate the apparent specific heat? Already I told you, divide the latent heat by the temperature range. Okay, if you divide the latent heat by the temperature range, so you will be having the unit also, it will be matching. Latent heat, it is kilojoules per kg. Temperature range, it is Kelvin or the degree centigrade. So kilojoules per kg degree centigrade means it is specific heat only. So divide the latent heat by the temperature range, you will be getting the apparent specific heat. You use it in this equation. Just now I told you, no, you use it in this equation. So if it is one dimensional, this will go up, but this will be staying. So what is that? You will be finding that you use it in this equation. So during the normal operation, okay, so during the normal operation, the CP value, it will be smaller. Sensible region, CP is smaller. So this equation will be, this temperature rise will be, this temperature rise will be gradual. And during a latent region, you will find that this CP will be rising faster. So what happened to compensate that? This temperature rise will be smaller. So that is the concept. Okay. So if you, one way of controlling the equation is by source. If you reduce the source, the speed of the equation will fall down in the phase change region. The other one is if you increase the specific heat capacity, automatically then the speed of the equation will be falling down. How you are increasing the specific heat capacity? So you give the specific heat capacity as a function of temperature. Okay. So you know your phase change temperature is 30 to 32 degrees centigrade. For 30 to 32 degrees centigrade, you raise the specific heat value. If you raise the specific heat value, so when this equation is getting solved, so it will gradually, okay, so again we will go here, so for better understanding. So it will be solving gradually here when 30 degrees is reached, okay, when 30 degrees is reached, so then the property will be changing. So the CP will be now increased CP value. So what happens when CP is increased, dou T by dou T will be decreasing. So here this is T, this is T, dou T by dou T is decreasing. That is what we want. So that will happen here. Okay. So very simple. So when you understand the dynamic of the equation, so this concept is very easy to understand. Okay. When you understand the dynamic of equation, okay, apparent heat capacity or the or your enthalpy porosity method, so it is easy for you to understand. Okay. Okay, fine. So these two methods are used. So this is the how you will be having. So while giving the specific heat also or apparent specific heat also, you can give it over a small temperature range, or you can give it to a wide temperature range. So here you can see if you are giving it to a smaller temperature range, it will be almost like a crystalline substance. If you are giving it to a wide temperature range, it will be like a organic substance, phase change material. It all depends on your what type of material you are seeing. Okay, suppose your phase change material, if it is changing its phase in 4 degrees, then there is no other go. You have to take this phase change temperature range as 4 degrees only, and correspondingly you have to calculate what is the. So though the latent heat may be same for all this case, the latent heat is same, but the temperature range is different. So here you can see if the temperature range is 1, then the latent specific heat is very much higher. Okay, and if the temperature range is 2, the specific heat is reducing. If it is 4 or 2, okay, so again it is increasing. So what is that you have to understand? So the latent heat is constant only. For any material, latent heat will be same. Okay, but the specific heat whatever you are taking, okay, apparent specific heat. So you have to mind the temperature range. If the temperature range is more, okay, then your specific heat will come down, because the equation is like specific heat is equal to latent heat divided by temperature range. The temperature range is more, automatically your specific heat will be coming. Okay, how you are going to do this in your solver? Very simple. You go to the solver, specific heat will be there. There will be provision for giving the specific heat as a function of temperature. So you can give the specific heat. like for our problem, what I told, so you give a less specific heat. Greater than 32 degrees, you give the liquid specific heat. Between solid and liquid, that is 30 and 32, you give the specific heat corresponding to two phase. Okay, so that specific heat, how you are going to get find out what is the latent heat value, divide by the temperature range. For our case, it is 2. So latent heat divided by 2, you will get the specific heat. So those two values you have to give. So like this here. So one value you have to give it here, and another value you have to give it here. Okay. So if I give it like that here, so then I'll be getting the solution. So if I'm having a step in the specific heat value, usually there may be some problem when it is coming to this temperature and then it is shifting suddenly. There will be some problem. If you are going for CFD solvers, there will be some trouble will be there. So if you don't want to do that, you can go for a triangular profile. So if there is no step, the property variation will be gradual. Okay. So then what happens? Your solution will be gradual. Or what you can do is you can have a small temperature step here instead of just giving, because see at 30 degrees you will have two values for CP. You will have a solid CP value as well as the highest CP value. In the same point, you cannot have two values. Similarly, at liquid S, you will have liquid CP value as well as the highest specific heat value. In the same point, you cannot have two values. So that means that is trouble. Okay. So what you can do is, for example, you can take 30 point, for example, 29.99. You can give the solid value. Then 30, you can give the latent heat specific heat value, that is apparent specific heat, you can give it. Similarly, when completing 32, you can give some value, that is latent heat divided by temperature range, that value you can give it. 32.01, you can give the next value, that is liquid specific heat. So that is how you, if you give that, the solution will be smooth. Okay, so that is how we will be giving it the apparent heat capacity method. So this method, okay, so this method in CFD, so I have done that. Okay, so I have done that. Okay, I am the first person to do that in the CFD. Okay, so I have a paper at 2010. Okay, so you can refer that. So I was the first person to do that in this method. Okay, okay, so okay, so now you know how to model the specific heat. So the same thing it is given, okay, in different forms. Okay, so the same thing is given in different form. Apparent heat capacity method, it is a C effective or apparent heat capacity. Okay, I'll have transient term and the deficient term. So you can have the values. Okay, you can have the CP. If the temperature is less than the solidus temperature, CP is equal to solid specific heat. If the TP value is greater than the liquid, then CP is equal to CP liquid. Okay, and if it is in between phase change, during phase change, latent heat divided by the solidus liquid, that is the temperature range, then you have a solid region and I have the liquid region. Solid region is 1 minus F into CPS, liquid region is F into CPL. Okay, and CP, okay, CP I can write it as 1 minus F into CPS and FL into CPL plus L divided by this. So I am accounting for the specific heat as well as the change in the CP value, physical CP value. See here the CP is not there. We are calling it as apparent. We are calling it as apparent here specific heat. There is specific heat is not increasing. We are taking as if the specific heat is increasing. So we are getting the solution. So we are happy. But really speaking, the liquid, the PCM will be in a two-phase region. Properties I have to take it in two-phase region. So that means for solid using the melt fraction. Okay, so the, 1 minus F into CPS. This is a liquid fraction. I'm sorry, liquid fraction. So liquid fraction into liquid specific heat and solid fraction. 1 minus FL is solid fraction into solid specific heat. This value plus this value plus this. Okay, plus apparent heat capacity put together, it will give the CP correct value. Similarly, for other property changes also we have to accommodate. You can accommodate for the change in thermal conductivity. Okay, that also you can put it in this form inside the phase change region. Then your solution accuracy will be good. Okay. Yeah. So change in density. Density also will be changing like this. Specific heat will be changing and the thermal conductivity will be changing because these are all the thermal properties. Okay. So that we have to take it. So this is how we have to do. So I have the temperatures, I have the specific heat value. So within the 20 for this example it is 25 and 28. So 25 and 28 you will find a jump in the value. So here you can see there is a jump in this value. Okay, so this if you give, that is sufficient. But if you are going for design builder, okay, so in design builder, so the arrangement is like this. So they are not going for apparent heat capacity, but the concept is same thing only. They are directly calculating the enthalpy value. Okay, so instead of specific heat, they are directly calculating the enthalpy value. How they are calculating? So we are calculating Cp between these two values. They are multiplying by temperature. That's all. They are multiplying by temperature. So that is how they are calculating. So your governing equation is like this. While solving the, instead of temperature, you are solving it as enthalpy, Cp into T. Okay, and we are having the data of the enthalpy, and you know that the enthalpy value will be higher in the phase change region, because if it is less than, H is less than 0, it is in the solid region. So it is uh, Tm plus H divided by Cp. Okay, and if it is a melting region, it is temperature is T. I'm sorry, I think here I have to give. So if it is in the temperature is less than the melting temperature, your H value is Cp into T minus Tm, melting temperature. If it is greater than that, so then my value is Cp into T minus Tm plus L. So what is the meaning of that? I'm giving the latent heat. Okay, latent heat is Cp into 2. So that is how enthalpy will be same. You know, enthalpy and latent heat will have the same unit. So Cp multiplied by temperature range, it will get the same value. So if you want, you can include the superheat range. Melting range or liquid range also. In liquid, what is the value? So that will be this value plus whatever the Cp corresponding to liquid into the temperature range. So that is how you will go. And okay, you are solving. So you will be getting enthalpy at various time steps. How to find the temperature? For finding the temperature, you have to go in the reverse. From here, you have to calculate what is the temperature. Okay, T from this equation. So this will work out like this. T will be Tm here, and if it is H is greater than L, so that is in the liquid region. Okay, so H is less than in the phase change region, the temperature will be melting temperature. So this is for a constant melting temperature. This formula is given for constant temperature. So for our case, there will be a melting temperature range. Solidus and liquidus will be there. So the simple concept, what you have to understand is you have to give the enthalpy as a function of temperature. Even in design builder also, we will be giving the enthalpy as a function of temperature only. Okay. So here you can see. Okay. So when I'm going to the so this is a bio PCM, a material which is given. Okay, a material PCM which is given. So in this you can see how the 1 minute. Yeah, bio PCM is here. 1 minute. Yeah, now it's working. So when you are coming here, you can see you are giving the. It is possible to give the value. So for each temperature of our operation, I have to give the enthalpy value. Okay, so here you can see some 16 points. For 16 points, they are given the enthalpy value. So that means for minus 20, it is 1. For 0 degrees, enthalpy is 8. For 10 degrees, the enthalpy is 16290. So that means if it is increasing suddenly, means what is the meaning? So it meaning that it is going into phase change region. So 15, 27, 20, 36990. So if it is going to 23, 24. So in the phase range region, so the value is included. Okay, the value is included. Okay, so the latent heat is included. Okay, so latent is included. So at the 16th, okay, so at 100 degrees centigrade, what is the enthalpy value? So in between itself, we have included the enthalpy. Okay, so that is what we have to understand. So that means that inside that we can go and we can change the value. So we have to give for whatever the corresponding temperature, we have to give what is the enthalpy value. So that is in the edit option, you can go and you can give for your own material also. So that is possible. Okay, that is possible. You can give it. Okay. Okay, we will go back to our discussion. So how we are giving the enthalpy value? So the for solidus temperature it is Cp into T. For liquidus temperature it is Cp into T. But in between it will be the Cp value plus latent heat. Okay. So for each value of latent heat, okay, for example, at 50%, it will be 50% latent heat I have to take. Okay, only 50% would have been melted. So similarly, 25%, 25% into latent heat. So that is how I have to add everything. So H value with the temperature. I am having H value with the temperature. Okay. So from that, okay, I am having H value with the temperature. I am finding out. Okay. So I am finding out what is the, and I am giving this plot only. I am giving it in the design filter software. Okay. So that means the latent heat will be there. Okay. So the latent heat will be there. So at each point you can give the latent heat. So from the solidus temperature till the liquidus temperature, you can give the latent heat. So that is how you will be giving the thing and we will be solving. Okay. Quick case study we will go through, then we will complete. Okay. As quick case study we will go through, then we will complete. Okay. So we have done in a design builder solver, we have taken a model building and we have done. Okay. So this is the ambient temperature. This is a solar radiation, measured solar radiation in the room. And we have in the lightweight, we have done with, for a building with PCM and without PCM. So that means this building in the wall we have given PCM. One simulation we have run for the same day, and without PCM also we have run. Okay, so this is how I am getting. Okay, so this is what we have without PCM. Without PCM, the temperature is higher. Okay, the variation of temperature is higher. With the PCM, so the temperature reduction is there. Okay. Okay, so this is about the temperature. What is about the heat? Heat. So the heat, okay, heat entry if without PCM, okay, this much amount of heat is entering into the building. So with the PCM for a lightweight building, so this is less, it is reduced. So now these studies you can be done. Okay, so this has been done in design builder software. Okay, and for a medium weight building, okay, we have done the same thing. Just we have changed the wall to be a medium weight. So in that we have integrated the PCM. Okay, and what is the temperature variation? So we have found that the variation in the temperature is higher. Okay, but one more interesting thing what you are finding is this is without PCM and this is with the PCM. Okay, with the PCM we are having a range, and without PCM we are having a constant. So what is the reason? Because of the phase change temperature. Okay, the phase change temperature, if it is moving freely like this, it is that means the phase change temperature may not be matching. So because of that, if it is in the liquid region, so the temperature swing will be there again. Okay, so that is the thing. Okay, so that means this is also possible. Okay, with the PCM, temperature range is also possible if it is in the liquid range only. That means you have to select the PCM with the correct temperature range. Otherwise, a problem like this will be there. And okay, now you can see without PCM the heat flux is this much, and with the PCM the heat flux is this much. And okay, so this is how we have done. So this drawing, whatever I shown, it is from that paper only. So you can, I told what are all the inputs what we are giving. Climatic input, T ambient we are giving. Now you see apparent heat capacity also it is added. So if you are going for phase change integration, okay, so you have to give this property, apparent heat capacity you have to give, then only you can give it. So we have done with apparent heat capacity. If you are going for a design builder, it will ask for enthalpy, temperature temperature enthalpy history you have to give it. Okay. Okay, then we have done the same thing with MATLAB. So we have written code. So this is for calculating the day of the year. Given the number of day, you can find out what is the declination angle, and given the hour of the day, you can find out what is hour angle. Okay, and you can find out what is the solar flux at each location, at each phase. You can find out Q. Okay, so then you have to. This is our governing equation. So in that we will be giving the thing. CP we will be changing the CP value. CP alone we will be changing. We have changed the CP value alone. We took that the CP is a variable. the apparent heat capacity. So that for the temperature, in the temperature range, the CP value you have altered. Okay. So you can see this is how it is altered. So solid, below solid, it is we have taken the specific heat of solid. Above liquid, we have taken specific heat of liquid. So between these two, okay, so I have the specific, I have a higher specific heat. Okay. So this is how I am giving to the solver, and I am taking an ambient temperature model also input. This is for done by MATLAB software. We have written the code in the MATLAB software. Okay. So this is how they have the building. These are all the building dimensions. We have given the properties of the materials. So that is very important. We have done the experiment also for this with our collaborator. Okay, from Meenakshi Engineering College, we have done the experimental validation also. So you can see along using MATLAB, we have found out the temperature history. So for east wall, you can see when it is entering inside, so the variation of temperature is like this. Okay, and after that, what is happening along the depth of the wall? Okay, along the depth of the wall. So you are feeling this peak is getting reduced. So this is the depth of the wall. Okay, 25 centimeter thickness. It is the depth of the wall. So what is happening if, as I'm increasing the depth of the wall, you are finding that the amplitude is reduced, and also you can see the peak is shifted. Now here the peak is at this point, maybe at 12 o'clock or much before that, because it is east wall, 11 o'clock, and but the peak is there in the evening only. You can see around 4 o'clock only. East peak is there at 4 o'clock only. It's very interesting. Okay, and west wall. What is happening in the west wall? So west wall. So you see after first of the west, the peak is there, but there also as when it is entering into the room, okay, along the depth, what is happening? The amplitude is getting reduced, but the peak is moving. Still, it is moving to the night time. Okay, 8 o'clock, 9 o'clock, like that it moves. And the north wall, what is happening in the north wall? Okay, so in the north wall, the reduction is smaller only. The amplitude reduction is smaller only. Okay, and then still it is peak is shifted, but still it is shifted. You can see 1 or 2 hours it is getting shifted. Okay, south wall, the reduction is more. Why the south wall reduction is more? Because south we have radiation, so that is why it is happening like this. But in the north, what is happening? It is because of ambient temperature. So the shift is not appreciable. Okay, it is because of ambient temperature. And roof. So roof, you should have seen that roof will have a lesser transients because solar radiation directly will be falling. And here we have taken a slab roof only with a smaller thickness only. So that is why directly the heat will be entering into the building. Okay, so that you can refer when you are. So this is the input what we are given to the simulation. And here when I am coming to the simulation, here you can see for the roof, this is maximum. This is maximum, and it is near 1 o'clock only I am getting the peak. For other things, the peak is getting shifted. For other walls, the peak is getting shifted. But here I am getting at 1 o'clock only. Okay, so that also you have to note it. So we have checked with the experiment also. So it is matching. And okay, so we have done for 2nd March. Okay, and we have done for 11th June, and we have done for 2nd September. We have done for 26th September. Okay. And we have calculated the performance parameter. Now we have introduced a new performance parameter for integration of PCM in the building. Okay, so we have submitted this research for the journal. Okay, so we find, okay, so it is a non-dimensional parameter. So we find in the March, okay, with this phase change temperature range, okay, the effectiveness is around 78.37. Okay, if I am giving it in roof and wall, effectiveness 78.37. In roof and wall, for June, it is very good, 91.4. Okay, so in the September, 78.79, and December it is 72.41. You may be wondering, same phase change materials, how it is giving different performance. So the reason is, whatever the phase change temperature you have taken, it is helping in the month of June, because June will have a diurnal variation. Maximum diurnal variation will be there. It is June solstice. And your PCM you have selected based on maximum only. So that is why it is performing better in that month. Other month, it is not working properly because that temperature range is not matching. Okay, so that is what we have found out. Okay, so likewise, this is for we have done for Chennai. Like this, it can be done for any location in India. So in fact, we have done for 5 locations in India, and we have submitted that paper to the journal. Okay. So, okay, so yeah, that is how we conclude. So we have created 2 models. So one we have done by Design Builder. The other one we have created our own model using MATLAB. So and we have found out a performance parameter for PCM integration in buildings. Okay, and so this work it has been done with DST. Okay, DST help. Okay, so DST funding. So in our research lab, we are doing the simulation. Our counterpart at Meenakshi Engineering College, they are doing experiment, and other counterpart, they are doing it at Anna University. Okay, so this work it is a collaborative work with Anna University, Meenakshi College of Engineering, and Ishrae Engineering College. So we thank the DST for the funding given for this work. Okay. And these are all the reference. Thank you. I think I have taken some extra time because it is because of our project. Thank you for joining. If any question is there, I will answer. So you can put your questions in the chat box. Okay. So is it possible to start the 6:10 to 6:15 so that we can finish on time? Okay, it is possible. Okay, but if you are joining, but Mr. Shah will come at 6. Okay, but others, whether they will come or not, I don't know. Okay, so others also you can put in the in the WhatsApp group. Then we can finalize. Okay, so if everyone is coming, I don't have problem. Okay, even I can come at 5:30 or 6 also. I thought that most of you will be working. Reaching home, it will take time. So that is why I've taken that 6:30. Okay. Yeah. So any question is there? I'm here to answer. So any question is there? No question. Have you understood what I taught today? Okay. So then tomorrow we will start at 6 o'clock. Can PCM be designed and manufactured according to the requirement? Yeah, it is being done. Okay. So it is possible. So we will be having some organic substances which will be changing its phase at different temperatures. So if you want any temperature in between, you have to take a mixture of 2 other. For example, you have a material which will be melting at 40 degrees. I'm sorry, 35 degrees, and you have another material which is melting at 30 degrees. Suppose if you want at 33, you can take as much material. Okay, and if you mix it, these 2 materials, so you will be having a material which will be changing its phase at 33. So that is what is done. Okay, manufacturers they do that. Yeah, it can be done according to the requirement. And I think there is a Plus Polymer. Okay, Delhi. Okay, so they are manufacturing phase change materials in India. Okay, but we have to make the selection. It's better to go for simulation before actual integration. Otherwise, if the selection is not proper, then your PCM may not even work. That is very important. Your PCM may not even work. Okay, so that is the problem. How we can analyze various insulation material impact on heat capacity and the thermal effect. Okay, so I will tell you, insulation is something different. So insulation is like it is the thermal resistance. Okay, so it is associated with the thermal resistance. It will reduce the temperature only. Or I can, for Kunjan Kumar, I will show this PPT. I think I have discussed that. 1 minute. Yeah. So here you can see what insulation does. Insulation just it reduces the peak. It will not shift. For example, if glass wool insulation is there, or some other insulation is there, polyurethane foam, or some other underdeck insulation of polyurethane foam, thermocol material. So all these things it will reduce the peak only. So here you can see it is reducing the peak only. Okay. But what storage material will do, or a high heat capacity material, what it will do, like a PCM or some material or a a building with a larger wall, what it will do, it will not only reduce the peak. See here, it is not only reducing the peak, it also it will also uh, shift the peak. How it will, whether it will reduce the peak or not, because even a storage material will have its thermal conductivity. For example, PCM, it is a storage material, but it will have a lesser thermal conductivity. So what is the meaning? So it will reduce the peak as well as it will shift. So both are possible. Okay. You compare this with concrete material or building brick wall material. So brick wall material, it will reduce the peak, okay, to lesser extent, but the shift will be there. Okay. But the PCM, its thermal conductivity is also less, CP value is also higher. So what it will happen, it will reduce the peak and it will shift nicely. So that is how that will work very nicely. Okay. So that will that means storage material, it will have two properties. One is thermal conductivity and CP value. If thermal conductivity is less, it will reduce the peak instantaneously. And if CP value is more, it will reduce the peak as well as the shift. So that is what. Okay. So it at all are dependent on the thermal properties only. Okay. So a combination of these two. Okay. A combination of these two. So it will both shift the peak, reduce the amplitude as well as shift the peak. So that is what we will do. Okay. So hope I have answered your question. Yeah, so I think I have answered your question. And various other methods. Suppose if you are going for the conduction transfer function method, just you give the property, automatically everything will be taken care. So in the conduction transfer function also, properties will be there. So there, if you go and give the property, automatically will change there. Because in the conduction transfer function, they are creating the parameters. For example, we have seen that B parameters, C parameters, all the parameters are there. So these parameters have been created for a specific. For lightweight, it is created. For medium weight, it is created. For heavy weight, it is created. So whatever the transfer functions for the lightweight, it will be different. Transfer functions for the heavy weight, it will be different. So that means just apply that transfer functions. Automatically, that will give you the correct results. It will give you what is the lag and what is the lag hour and what is the reduction in amplitude. So both the things it will give you. Okay. So I hope I have explained. Yeah, so already I told you. So you can go for McQuiston and Parker. Okay, so it has a comprehensive discussion on this conduction transfer method and radiant transfer method. Okay, conduction transfer function method as well as radiant transfer method, time series method. I'm sorry, radiant time series method. Okay, so McQuiston and Parker. If I will put it in the group, I think you can take it. Okay, I'll put the book in the group, so you can take it and you can study. Okay. So any other question is there, I can answer. Okay. Okay, so if there is no questions, thank you for joining. Okay, so tomorrow, as per the request of the participants, so we will start our discussions at 6 o'clock. Is that okay for everyone? If anyone have the problem, you can just put the message, post the message, or you can put it in the WhatsApp group. So accordingly, we will decide. So you want at 6 o'clock, we will have it at 6 o'clock, no problem. Okay. Okay, thank you. I think today's session was very big. Okay, so it's because I was just explaining about the problems what we are doing in our campus, or my DST problems. So that is why it has taken some extra time. Sorry for that, but the information should be useful for you. Thank you again. So we will meet at 6 p.m. tomorrow. Okay.